Hirata. I'm a professor of the Computer Science Department at Instituto Tecnológico de Aeronáutica, ITA. I'm going to talk about introduction of distributed transactions. Distributed transactions is a chapter of the distributed programming course CES-27, that is an undergraduate course, and CE-288, that is a graduate course. The outline for my talk in this chapter includes the following topics: an introduction where I will give some definitions and I will discuss a little bit about properties of transactions, and it also includes recovery in centralized system. That's very basic, is very relevant to understand the whole transaction distribution, and also present to you how you can support atomicity of distributed transactions. In this case, I'm gonna talk about the two-phase commitment protocol and the three-phase commitment protocol. The chapter 4 is about the concurrency control for distributed transactions. It has to do with consistency, how you can control concurrency in order that the transactions result in a correct execution. Okay, so let's start then with the introduction. What is a transaction? For this course, transaction is an atomic unit of database access, which is completely executed or not executed at all. You have to see transactions has a set of sub-transactions. In this case, you have to imagine that they are sub-transactions, for instance, in a transfer of some amount, for instance, $1,000 from account A to account B, can be seen as two sub-transactions. One is the debit of $1,000 from account A. Another sub-transaction is the credit of $1,000 on account B. The issues of transactions that are relevant to this course and are relevant, and I'd say, to having a correct result are two. One is recovery, because as you may know, the distributed systems, you have components and subsystems that can fail, so you have to consider how recovery will be dealt with. Another thing is concurrency. You have to sort of arrange the execution of the subtransaction in the operations so that the execution is correct. So you have to deal so with concurrency control. Let's start showing some properties that are very relevant and important that every transaction must meet. Before going to properties, you have also to define a distributed transaction. Distributed transactions are transactions that access distributed databases. What is the distributed database? Distributed database is a collection of data which are distributed over different computers of a computer network. So have to consider that the resources are distributed. You have to consider also that you have a network to access those resources. One thing is you have to think of is that each computer has autonomous processing, so they can decide, they can perform local applications. They can also, I would say, take part in different ways in a global application. So that requires accessing data at several sites using the communication subsystem. So you have a lot of, I would say, points of failure that you have to consider. You can have the hosts. You also have the communication subsystems in different links. So you have to consider, when you are thinking of distribute a transaction, you have to consider not only the distribute database, but how the distribute database you provide the service through the network, considering or taking into account the failures of the many components that you have in the system. Okay, and you have the concept of distribute transaction, you have the concept of distribute database. You know that all those transactions and database, they run in a communication and network. So you also have to consider that you have some agent taking care of that. Okay, in this case, you also that the management of distribute transactions is the job of this agent. Okay, the distribute transaction management is performing using several techniques. So since you have many kinds of issues to deal with, you have also to have many techniques. So we're going to discuss that will be part of the course as well. The recovery mechanism, the two-phase commit protocol. You also have to understand how the concurrency issue happens and how to control this concurrency issue. For that, you're going to use the two-phase locking for concurrency control. Okay. Having defined all those things, you have now you think you can start describing the properties that the transaction or distributed transactions must meet. A transaction is an application or part of an application which is characterized with following properties: atomicity, concurrency control, isolation, and durability. You can see these four properties as a set by acronym ACID. Okay, let's see the first one, atomicity. In atomicity tells that all the operations of the transactions must be performed at once, at all. I mean, we don't have just some operations of the transactions being performed, the others are not performed. So the atomicity means that either you have all the operations being performed or you have none of the operation is performed at all. So it requires that if a transaction is interrupted by a failure, its partial results are undone. Yeah. So if you have a point, for instance, in the transaction of the transfer, you cannot have just the debt on account A. Okay. You must also have the credit on account B. Otherwise, you have an inconsistent situation. There are two reasons why the transactions does not complete. One is the transaction abort. Another one is the system crash. Abortion of transactions can be requested by the transaction itself or the agent that is managing the transaction, the user, or the system. For instance, you can have some temporary unavailability of resources. For instance, the database is not available for a while. It's undertaking some maintenance. So in this situation, you can have an abortion. The activity of insurance atomicity in the presence of transaction aborts is called transaction recovery. Okay, and also you can have the end of a transaction by crash. In this case, you call the activity to ensuring atomicity. In this case, is called a crash recovery. The atomicity you can, once you have started a transaction, you can have either the transaction can commit or it can abort. That's in the normal case. Okay, so if the transaction is aborted, so you have most likely to undo all the operations performed so far. So that's something that you have to discuss when you have to proceed and terminate the transaction or commit the transaction. Another situation is when the transaction starts and the system for some reason crashes, so you have it forces an abort. For instance, you have some destruction, massive destruction, and where all the computers are held. For instance, you can have in that situation as well. Okay. The second property is durability. Once the transaction has committed, the system must guarantee that the results of its operation will never be lost. It means that the results that you have obtained, you will be sure that you further failures won't affect that result. So the durability is assured with log techniques and also stable memory storage. So what you have also to consider include is database recovery, is the activity of providing the transactions durability. The third property, which is very important, is concurrency control. Concurrency control, also known as serializability, means that if you have many transactions being executed concurrently, the results of this execution is the same as if they were executed serially in some order. And is serializability. In serializability, if several transactions are executed concurrently, the results must be the same as if the transactions were executed serially in some order. The serial execution of transactions is said to be correct by definition. So if you have, for instance, 3 transactions, you can have any combination T1, T2, and T3. Any combination of these 3 transactions is correct in terms of execution. The problem with concurrent execution is that the transactions are decomposed in sub-transactions or operations. So when you execute the operations of the transactions, you can execute in an interleaved mode. So the problem of executing in the interleaved mode is that you can produce a result that is not correct. I will show you with an example. Let's see this example. We have a transaction 1. That's a deposit of one and for instance R$1 on account A. The initial balance for this account is 49,999 reais. You also have another transaction T2. That's that you call interest payment on A. In this case, you pay 1% of interest if the value is greater or equal to 50,000 reais. You pay 0.5% if the value is less than 50,000 reais. And for these transactions, you have the operations R1, that you read the balance of the account 1, and you compute the deposit in transaction 1. That's then you write the computation as the operation W1. Okay. For the transaction 2, you have the read operation by the transaction 2 on account A, and also have in this case you have to write the updated balance, in this case given the interest rate either 1% or 0.5% of the value in the account. Okay. Let's let's suppose that the sequence is T1 and T2. If the sequence is T1 and T2, first you make the deposit, then you pay their interest. Since with the deposit you have the 50,000 reais, then you have to pay 1% interest. So in this case, the total amount, the balance, the resulting balance will be 50,500 reais. If the sequence is T2 and T1, what you do first is to pay the interest. So in this case, the interest will be paid using the 0.5%. Then you add 1 real. So in this case, the resulting balance will be this value, 50,000 to 48.995 plus 1. That's the deposit. So the resulting will be 50,000 reais, 249.49 cents. Both, by definition, both scheduling or executions are correct. The problem is either you can do one transaction first or you can do the other one. But what happens if you intercalate or interleave the operations? Suppose that you have this scheduling. The transaction 1 reads the balance in account A. The transaction 2 does the same as well. Then you have the deposit by account A, adding 1 real. Then you have the payment of the interest, in this case for the value that you have read in the transaction 2. Okay, that's not 50,000 but 9,999 reais. So in this case, you're gonna have this result for the balance. So this is inconsistent because this value you cannot get from the sequence T1 and T2 nor T2 and T1. So you call this a wrong computation. So that's you want to avoid. That's what you have to do is to put assure that the concurrency control mechanisms they will I would say keep all these things the execution in a correct order and avoid this kind of computation. Okay, and the fourth and last property is isolation. In isolation, you will say that the incomplete transaction cannot reveal its results that are partial to other transactions before commitment. This property is necessary because you don't want to propagate, for instance, some partial value that is not complete. So that what happens is you avoid somehow the problem of cascading aborts. It's a kind of domino effect. Okay, I'll show you with an example. Let's suppose that you have transaction 1 that makes a credit of value V to account A. Initially, the value is 0. So in this account, you have this computation. Okay. So you have the read, of course, of the value of A, and you add the value V. Then, if you don't do isolation, the A record can be read by other transactions. So in this case, you can debit value W from A. So if A is greater than W, so you compute A equal A minus W. So these transactions can commit. Suppose that the first transactions, you review the value. For some reason, it fails. So what happens is these transactions, you have to sort of undo the operations we did. That's the credit of value V. But these transactions, since it already read the value of A, so this transaction cannot be undone. So that's the inconsistent problem that you have by making those values or records available to other transactions. Okay. Okay. This isolation, with the isolation, I have shown all the properties of transactions that happen to be the same, the properties for distributed transactions. And the next class, I'm going to show you the recovery in centralized systems. Recovery in centralized systems is very important to understand the mechanisms of recovery in distributed transactions.